Have you ever wondered how Netflix just knows what movie you're going to want to watch next? Or how astronomers can possibly discover a new type of star in just a sea of data? Well, it's all about finding these hidden groups or clusters. In this explainer, we're going to pull back the curtain and see exactly how machines learn to find these hidden patterns all on their own. Okay, so take a look at this. On the left, you've got a vibrant, high color photo, right? And on the right, that exact same image, but it's been compressed down to just 16 colors. You can still tell what it is, but an algorithm has somehow taken millions of pixel colors and boiled them down to a handful of representatives. The question is, how? And that right there, that's the core mystery we're tackling today. How can an algorithm with zero human help look at millions of colors and just pick the 16 most important ones? And this isn't just about pictures, it's about finding the hidden structure in pretty much any complex data you can imagine. So, this whole challenge actually has a name. It's called the clustering problem. It's really the art of finding these hidden groups in data when you have no labels, no instructions to guide you. This is a classic example of what we call unsupervised learning, where the machine literally has to learn on its own. To put it simply, data clustering is just the process of sorting unlabeled data into their natural categories. The algorithm has to figure out what those categories even are on its own, based purely on how similar the data points are to each other. So, why do we care? Why does this matter? Because clustering is incredibly powerful. It reveals the hidden structure of our data. It automates categorization. And, like we just saw with the image, it's a fantastic way to compress data just by storing the average member of each group. And this has huge implications for, well, everything from marketing to medicine. All right, let's start our quest with an algorithm called K-means. It's a really great place to begin because it's simple, it's elegant, and it's super intuitive. It's honestly one of the most common ways to get started with clustering, and I think you'll find it pretty fascinating. The K-means algorithm is basically a simple two-step dance that just repeats until it finds a solution. First, in the assign step, every data point looks around, finds its closest cluster center, and joins that group. Then, in the update step, those cluster centers move to the new average position of all the points in their group. It's this constant back and forth until everything finally settles into place. Let's actually see this dance in action. Here are our data points, all in green. The algorithm starts by just making a random guess. It drops two cluster centers, the red and blue crosses, right into the mix. As you can see, they're not in the right place yet, not even close, but that's all about to change. And now for the first step, assignment. Each and every data point gets colored based on whichever cluster center it's closest to. And just like that, boom, we have our first kind of rough set of clusters. Next up, the update step. See that? The red cross moves to the average position of all the new red points, and the blue cross does the exact same thing for the blue points. You can literally see them inching closer to the true center of their groups. And the algorithm just repeats this two-step dance, assign, then update, over and over and over again. After a few rounds, the cluster centers just stop moving. They found a stable position, and that's it. That's how K-means finds a final solution. So simple, but really powerful. But K-means has a catch. For all its simple power, it uses what we call hard assignment. That means a data point is either 100% in the red cluster or 100% in the blue cluster. There is no in between. And that rigidity, well, that can be a problem. What if reality is a little bit more fuzzy? And this brings us to the next stage of our quest, probabilistic or soft clustering. We're about to move beyond the black and white world of K-means and into a world of nuance, of probabilities. And trust me, this is where things get really interesting. So let's ask a new kind of question. What if a data point could belong to both the red and the blue clusters? What if membership wasn't a firm yes or no choice, but a matter of probability? To think this way, we need a new concept, the latent variable. A latent variable is something we can't see directly, but we know it's there, influencing the data we can see. Think of it like someone's mood. You can't see mood directly, right? But you can infer it from their facial expressions, their body language. In clustering, the latent variable is the true, hidden group label for each data point that we're trying so hard to uncover. Here's a great way to think about it. It's called a generative story. Imagine an oracle is creating our data. First, it rolls a die to pick a cluster, let's say red or blue. Then it pulls a data point out of a bag of points that are associated with that color. But here's the catch. The oracle only shows us the final data point. It hides the die roll. Our job is to work backward and figure out which die was rolled for each point. It's like we're detectives in a data mystery story. And the tool that lets us do this amazing detective work is the hero of our story, the expectation maximization algorithm, or just EM for short. It performs a much more sophisticated dance, one that actually embraces the uncertainty of probabilities instead of demanding the certainty that k-means does. Now, just like k-means, EM has a two-step dance. In the E step, or the expectation step, it calculates the responsibility of each cluster for each data point. That's really just a technical way of saying it guesses the probability. Like, is this point 70% likely to be from the red cluster and 30% from the blue? Then, in the M step, or the maximization step, it updates the clusters themselves, and not just their center, but their shape and size too, to best fit those probabilistic guesses. Okay, let's watch this one in action. We start with some initial guesses for our clusters. But notice this time, our clusters are full probability distributions, represented by these red and blue circles. Now for the E step. This is my favorite part. Instead of coloring each point solid red or solid blue, we use a mix of red and blue ink. The amount of each color represents the probability that the point belongs to that cluster. So points that are clearly in one cluster are mostly red or blue. But look at the ones on the boundary. They get a mix of both, turning them this beautiful shade of purple. Next comes the M step. The red circle moves and literally reshapes itself to best fit all that red ink, and the blue circle does the same for the blue ink. They're basically moving to the center of mass of their responsibilities. And look, they don't have to stay perfect circles. They can stretch and change shape to better fit the data. This is where the real power of EM kicks in. After repeating this process, E step, M step, E step, M step, the algorithm converges. And the result is, well, it's beautiful. We end up with these nuanced, elliptical clusters that perfectly capture the true underlying shape of the data in a way that the simple spherical clusters of k-means never ever could. It's like going from a child's crayon drawing to a masterpiece. So let's just put them side by side for a second. K-means uses a hard all-or-nothing assignment, which results in these rigid spherical clusters. EM, on the other hand, uses a soft probabilistic assignment, which allows it to find these flexible elliptical shapes. At the end of the day, k-means is all about minimizing distance, while EM is about maximizing probability. And believe me, that makes all the difference. You see, in the end, the journey from k-means to EM is more than just a better algorithm. It's a journey from simple assignments to really understanding probability. The EM algorithm gives us this incredibly powerful tool for finding the hidden, the latent causes that generate the data we see all around us. It's like going from just treating the symptoms to actually finding the cure. And that leaves us with a final thought. Where else in our world are we only seeing the effects, while the true underlying causes remain hidden, just waiting for us to find them?